Hi, Con. Can you hear me? It's not really there. Okay, I can. Now I'm going to go back to .cam. There. Should be .cam. Except oh, yes. That sounded really bad. I guess that's okay.
Oh, it's probably got a motor.
Yeah.
I bet you can just.
It's definitely got a motor, but wouldn't it do that naturally? Like, I don't know, it didn't sound natural. So you have like log intensity, which you can take as like log mass.
Can you hit like autofocus? It should be like an autofocus.
Yeah, yeah.
Or brightness.
Auto. That worked. That's good, isn't it? That can zoom in, but that's good enough, isn't it?
Yeah.
Okay, so you can take it as log. It's actually I is going to be like the mass times the number. So it's going to be like the concentration and the mass. Right? So, and then, but since our concentration is fixed, it's the mass. And then Q is going to be 4 pi over lambda sine theta, or theta by 2, depending on how you want to do it. If it's 2 theta, it's theta. Anyway, Bragg's law and those lexicon is that Q's 2 pi over d, because d is lambda by 2 sine theta, or theta by 2, 1 pi to theta. That's Bragg's law, like for diffraction. That's like the fundamental. If you get a diffraction pattern, you have like intensity and then 2 theta usually. And there'll be a bunch of spikes, and you get the spike, it's a 1-1-1 plane. You use this law to get the d spacing. It'll be like 1-1-1. And so anyway, so Q is kind of like they ask, why did you plot against 2 theta? So why didn't you plot against d? Like just size, that would be easier. So theta is experimental, so Q is like a compromise kind of. It's 1 over size. Right, so this is a plot of size kind of. So say mass and size, that is the fractal dimension. So if it's a rod, like the longer the rod, the bigger the mass and the size is longer. So there's some things that only have one answer, like 1 is a rod. There's only one answer to it. And 3 is kind of like a 3D object, so like a sphere. It's like the most common one, the one that physicists like. Right, between 1 and 3, you can have different options. So you have like 2 can be a Gaussian chain, or 2 can also be a disk. Right, so 1 has only one option, 3 kind of has only one option. 1 really has only one option, like it is a rod. That's it. Right, 3 could be different shaped 3D objects. So like in proteins, 3 could be a native state protein that's got like the right shape to function, or it could just be a blob. Right, so it could be like something that could save your life, or something that's going to do nothing. Right, so they're both 3D. Anyway, so the 2 has 2 options. You can say, like, if I put a current across this, what's the dimension of that path? And that dimension would be 1. So you say the minimum dimension for that thing is 1. And this thing, if you put a current through it, the dimension of that path is going to be 2. So there's 3 dimensions. There's df, this dimension of the kind of the density. Right, so you have like mass goes with size to the df, and then the volume goes with size to the 3. So density is size to the df minus 3. Right, so if you're in 3D, the density is fixed. It's a fixed value. If you're in 1D, the density rapidly decays. So what does that mean? Like, that means if you take the rod and you spin it around, the density of that, if the rod's really short, it's got a higher density than if it's a long rod. So it's kind of like the density of the object spinning in space, like the space that it can eke out. becomes clear, like the density of a polymer coil, because it already is kind of spun around. Right? So anyway, if it's a 2-dimension, the density decreases with size by power 1. So like for polymer coils, the bigger they are, the less dense they are. So this dF is really a density dimension. It's called the mass fractal dimension. This is the minimum dimension, and then it turns out that dF is made up of this short circuit dimension, and then another dimension C, which tells you what the thing is. So if you take dF and divide by dmin, you get C. The polymer is a linear polymer. 2 divided by 2 gives 1. So it's a one-dimensional object that's been crumpled. So dmin is like how crumpled. C is what was crumpled. So you take a sheet of paper, a flat sheet of paper, it's 2, 1, 2. And then if you crumple the paper, well, you can only crumple it until dF equals 3. So the most dmin can get is 1.5. So your crumpling action can go from 1 when it's a flat sheet of paper to 1.5. It can't go more than that because you can't compress it to more than 3 dimensions unless you're in 4-dimensional space. So I mean, people talk about different dimensional space, right? But anyway, that's kind of the way this works. With these 2 dimensions, you can say kind of what it is. And if you're at 1, there's only one thing. So for our thing, we have, let me go back here. So I did go through this, it's in the notes, believe it or not. So here you got 1, that's the blue line. So that's one-dimensional, that's a rod. The only thing it could be is a rod, and he's got a picture, there's a rod. So that's what it is, it's a rod. So, and this is size, so it's inverse size. You get the big size over here, small over there. So the rod is going to end at some point. It ends at the length. So if you take 2 pi over that Q kind of right here, that should be the length of the rod, right? So this is called looking at things in inverse space, okay? So you're looking at a rod in inverse space. It looks like this. So it doesn't look like anything you're used to. That's how it is. Basically, it's like a different language, and you need certain touch points to interpret. And the power laws are like the main touch point. That's the main thing where you can say what's reality. So power 1 means it's a rod. That means the largest thing to the left, which is larger to the left, is the length. Then over here, where you start to see these oscillations, that's the spherical vesicles. Right. So that's the radius of the spherical vesicle. In between, it's power 1, it's a rod. When it kinks up, dmin is going up. So he gets 1.5 for the red one, the green line. That means it's a kinked rod. I mean, it could be a kinked rod. It could be other things. It can't be a sheet because it's less than 2, right? But it could be other things besides a kinked rod. It could be a branched rod, for instance, or it could be something else that you can't imagine. But one thing it could be is a kinked rod. Right, so it doesn't tell you exactly, but it's consistent with this cartoon that he has. So that's good. Then again, like 1.5 scaling, I mean, it's consistently kinked the same way from the smallest size to the largest. And then the end point is where that 1.5 ends, which is about like here. So it tails over. Right, the tailover thing, I'll talk about later, but basically the tailover thing is kind of a general rule. Okay, so you say, if I shoot a beam of something at something that comes out, then it's going to come out, and I say, well, it's Gaussian. So I have like my intensity, and then I have Q, so I have plus Q and minus Q. I have 0Q. So 0Q would be infinity because it's 1 over size. That's just kind of a weird place, but say you could get to infinity, and then it's going to be Gaussian. So then I'd say this is going to be Gaussian function is Q squared, and it turns out that this is the law. So you need a number. This argument has to have no dimensions. So you need a size here. So RG squared, the raised to gyration squared, is a number that gives you this Gaussian shape. This is a linear plot. If you do log I log Q, then it looks kind of like that. That's what this Gaussian would look like. So you can get I naught. That's the thing that has to do with the mass and the number. And then you get this tail over, that's this radius gyration, and at some point it's going to have like a power law, a rod. Right, so it turns out like RG for a rod is the length squared by 12. And plus the thickness, plus the radius squared divided by 8, I think. RG squared, right? So there's an equation for a rod for what that RG would be. It's got components of both, but it's basically the length because it's L squared. If L is bigger than R, it's going to be like a huge number compared to that. So you can think about that one. It's basically RG has to be the length. I mean, there'll be another like tail over kind of here that has to do with this one, and that's like that the radius is like RG over 2, squared over 2. So you're going to get something like that out of it, you know, break apart. You're looking for these like kind of needs and straight lines. Those are the two things you look for. Anyway, so that's kind of one thing in this. Then I think that's a question. That's one of these questions, like just says there's a lot. Yeah, there's kind of a lot in here. This thing, all right, this is from this book. Okay, so this isn't the same equation from class. The book I gave here, so I just linked it here. So if you click this, then you have to put an F at the end. And then it's going to be on page like 127, I think. 228, pretty close. It's like, all right, where did I put it? Here. So if you go to 228, he derives it. This is the reference from the book. 228. So you can't search in this PDF for some reason, but he's got a chapter on persistence. That's not really 228. Huh? That's 220. That's 228. So there's that equation 6.4.11. And then he derives it right here. Right? So you can just copy that if you want. Or anyway, if you take that equation, it limits to the same. So if L is really big, right, then this is a small argument. So exponential minus 0 is that's not going to work. As this gets larger, this gets smaller. This goes to 0. That's the idea. L is big, this thing goes to 0. Then you have 1 times 2LP squared. And so you have LP and 2LP, and then it's capital L and LP. Capital L is the contour length, and that's much larger than LP. If you have an infinite change, this term drops out. Then you just have that term. And this thing also equals L times LK, because it's NL squared, NK squared, LK squared. That means that 2LP equals LK, because the capital L's cancel. So that's the same argument from in class, but it's like the equation's a little bit different.
Say that again. What did you set the contour length to?
The contour length is big.
Right, but
That's like the chain. Like if you stretch the chain out, what will be the length of it?
you say it was NL or NLK?
It's here. So we had like R squared equals R dot R, right? I and J. And then we said like I could equal J. If I equals J, then there's N of those, and it's going to be R squared. And then if I doesn't equal J, if it's random, then it's just as likely to go forward and backwards. So they cancel out at 0. So you just have this thing. So R squared is NL squared. That's the definition of the Kuhn length. That this thing is going to be 2LP times L. This thing equals L times LK, because NLK is the same contour length. So NK LK equals is capital L equals NPLP. It's the same chain, stretched out the same. So those terms drop out, and then they just have LP is 2LP. But that means you have to have a big chain for that to work, infinite chain. Also, this whole thing, this is a Gaussian assumption. This idea that it's random goes to zero, that's Gaussian. That means it's a random distribution. It's a chain that can pass through itself, right? So because it's random, so it ignores anything like that. So that kind of we went through too. So in some ways, it's like a trip down memory lane here, but yeah.
Sorry, the NP, I understand that's the number of like backbone sort of residues that you have.
Uh-huh.
The NK, is that just the number of sort of like orientations within the backbone?
All right, so the n's just an arbitrary number. So it's like if I made polyethylene, I could make it from this guy, ethylene, or I could make it from like this guy. So I could just polymerize that thing, right? So that would be my monomer. So I'd have like, say 3 of those and have a molecular weight of like 2000 or something. Or I could say that one, and then I would have like 30 of those and have a molecular weight of 2000. Right, so this N, the chemical N doesn't have any meaning. It's just like whatever the chemist decided to use as a monomer. Right, so then there's a physical thing that happens. There's 2 ways to look at that. One way is you say that it's a Gaussian chain, and then I can measure R squared, so I can measure that number. I'll show you how you measure it later on, but actually, we know we can measure rates of gyration in the scattering, and RG squared is going to be that R squared divided by 6. So we'll derive that later. But basically, that's one way you measure it, right? So if you can get R squared, and then you can say like it's going to be, if it's going to be Gaussian, it's going to be this Kuhn thing. That won't equal. That doesn't equal the number of bonds times the bond length squared. There's a number that relates those two. It's a C infinity number because again, this is NLK is L, NB, LB is also L. So this is just LK to LB, and that's what C infinity is. It's like how much it amplifies the bond, the characteristic ratio. I mean, for an infinite molecular weight. Anyway, there's a lot to it, but basically the N depends on what model you want to use. It depends what L is. So it's kind of like arbitrary, right? So anyway, for LP, it isn't really doing this Gaussian thing. So Kuhn was a rheologist. He needed this unit to talk about the flow of the polymer chain. So he kind of came up with this business. The persistence idea came from Austria. So Kuhn was, I think, Swiss. They're right next to each other, but they're quite different places, kind of. Well, they both ski. Anyway, yeah, they really think of themselves as different. They both speak German partly. The Swiss speak French, German, Italian, and Romanish or something. So anyway, but the Austrians, who knows? But the Austrians have a certain kind of feel to them. It's very like, I don't know, masculine, domineering. Like Hitler, who was from Austria, put it that way. And that Austrians still kind of think along those lines. Like they never really. The Germans like are different than that in a sense. So anyway, the Austrians came up with this persistence-like idea. It was Kratky, and then a guy named Farad. Those two were like geniuses, and they kind of came up with this thing. Kuhn was a rheologist. He was like kind of a grunt, I guess. And it's like sticking stuff in, watch it flow. He needed a number, so he got it. Anyway, so that's kind of, this is all in the 50s, I guess. So that's kind of it. Did that answer the question? The N the N depends on the model. So if you want to use a Gaussian model, you have a Kuhn N. The persistence has to do with this wiggly chain you talk about, just like a gas atom. So with the kinetic theory of gases, it has a persistence length. So Kratky and Perrod took that persistence length concept from gas atoms flying around and then said, this chain is flying around too. It has a persistence length. So they really were biologists, kind of like they were working with biological materials, and Kuhn was working with synthetic polymers. So it's kind of a little bit, the persistence length is popular in biology, more popular, and the Kuhn length is kind of more popular in synthetic polymer. Although they use this 2 number to match them. Anyway, hopefully that answers that business. Then what else is in here? This doesn't exactly have an answer, you know, this business of, he finds so the idea is like he's making these beads that are positively charged and he's got a negatively charged. So he's saying like they have to match up, like the plus and minus have to match. That's the magic place. It should be 0.5. So you'd get something like this. Number Z would be 0.5, would be minus over plus, plus minus. But he finds that the magic place where they actually match up is 0.7. And he doesn't explain why, because he doesn't know. But it happens no matter what, no matter if he uses the stiff chain or the flexible chain or some other chain, it always happens at 0.7. So this is just saying like why, explain why in the context of this cartoon that he has here. So see if you can make that cartoon work for that 0.7. Like the cartoon won't work for 0.5, I don't think. So maybe, but I think the cartoon kind of points you in the direction of less than 0.5, not bigger, the way I see it, which could mean that the cartoon's wrong, even though this thing kind of supports it. So there's 2 things that don't support the cartoon. One is the 0.7. And the other thing is this little ditty that he stuffs in. So the organization of the plots, you might have put them in a different order depending on what argument you wanted to make. Okay, so like this is something about the order here. This one he stuffs in. So this is how many spheres per molecular weight of the chain. So if his cartoon's right, that should be the number of spheres is proportional to the number of the length of the chain, right? Because it's a rod. So they have to go, if you add double the rod, you should add double the spheres. That's the dashed line. Right. I don't know what the green dashed line is, but that's the dashed lines here, power 1. He gets power 1/3, which means that the cube of the molecular weight gives you how many, which you can't get no matter how you think. It should be the how many cubed, should be the other way around if it was just a glob of stuff. So 3D. So it's like going in the wrong direction. Could be that this isn't even a decade, so it might not work. But anyway, come up with a model that would explain that 1/3 thing. Like what, how could you draw a cartoon like his original cartoon that would explain that? It might not be possible. It might be that it's just not true, you know, or the measurement's wrong, who knows. He's using different techniques. Like this is neutron scattering. Then he uses dynamic light scattering to hydrodynamic radius, and then he uses static light scattering to get the number of spheres. So he uses kind of 3 different techniques. So it might be that they don't agree with each other, or the samples were different, who knows. But basically that's what he reports. He gets that the persistence length drops with the charge, which could be screening. So he had like you got to keep in mind that we have this business that we have the persistence length, we have the device screening length, and then, which can also be lambda or something else, so some other symbols, 1/kappa. And then we have this charge spacing, right? So we have there's 3 lengths for the polyelectrolytes that we're considering. So the screening length goes with the charge density. So that number that he has to the 1/2, 1 over that. So the higher the charge density, the smaller the screening length. And with this, that means if the screening length gets too small, say the screening length is an angstrom, then there's no charge, like the charge disappears. Then the spheres just float off free. So there's an issue that there's 3 things you're considering, not 1. It's not just the persistence length. So already you know the persistence length decays with this charge. with Z, which is the ratio. It's like minus over minus plus plus. So you already know that LP drops with that. So basically that kind of means that this number is changing, I think. So maybe he's not accounting for it. I don't know for sure, but he doesn't say, I don't think, but he's not keeping a charge balance in it. So he's actually adding more counterions. The more counterions you get, that number gets smaller. Then when you have these charges repelling each other, all of a sudden, like those two would even repel, but now only those two repel. So the persistence length gets smaller as that charge, as the counterion concentration increases because the device screen length gets smaller. So the long range charges disappear. And then you want to see the local ones, so it becomes more flexible. If that happens, then that could explain some of the things he sees too. Like he doesn't consider the device screen length changing. The A is fixed. This thing changes with Z. So these things could all come into play to answer it. Or I'm not really looking for an answer. I just want you to kind of consider like what just to read it and kind of be able to say something about it, not something kind of coherent that has something to do with what we talked about in class. That thing, and then this is just take the numbers he gives for persistence length, take 2 pi over q, and then just map it on that scattering plot and see if they match up with the ends of the power laws. I think they do. I think it works okay.
I have a question about that.
Yeah.
So for like the hyaluronic acid,
Yeah,
its persistence length is 9 nanometers.
yeah,
So on that graph, 2 pi over that, 2 pi is like 6-ish.
yeah,
And so 6 over 9 is like 2/3, right?
Yeah.
0.66 or 0.7, it's close to there.
yeah.
Is it that graph or the other graph further on the paper? Or are they the same?
I'm kind of looking at this one. That one's given again. Okay, it's given in a different way here. Yeah, here it doesn't really show that power law ends.
Yeah, is it, I mean, 1 over like the 6 over 9, that'd be like 0.66. Is that not?
It's no, it's 90. 6 over 90 because it's nanometers. This isn't. Oh, this is in nanometers.
Yeah, this is what I
Oh,
was confused.
I
The
think.
numbers don't match up at all.
It would be at like the start of the.
If it was an angstrom, it would
Yeah, I was thinking this was angstroms. You're right. It's off by a decade then. Okay, well then they don't match. Then that's the answer. They don't match at all. Like that gives you further credence to say his model's not true, you know? But that's a big, if you're reviewing this paper, so you can't believe everything you read, you know? So if you're reviewing this paper, that would throw the whole paper out, you know? His measurements don't agree with each other. You can get the persistence length right here. I mean, it's right in this, not this green ones are hard, like that could keep going, but the way he shows it in the original one, it tails over. Like here, that seems to tail over to me. So basically, I'd say the
Go even
persistence length.
further to the. Are they able to measure further on that?
No, if it's 9, then this thing would go way over here, right?
Yeah.
Yeah, so yeah, that would be, so light scattering begins at 0001. So this is 00 and then one more decade. So light scattering's over here. He measures the light scattering for it, but he doesn't show the data.
They talk about it a little bit that there's a gap in the data. So when you finish the neutron scattering.
Oh,
it's
exactly.
Oh yeah, here, that's the
Okay, so
light
this-
scattering.
then there's a gap. where it
So if this is flat, he's already beyond the persistence length. Right, this would have to be power 1, and then it ends when you get to that knee thing. So the persistence length is smaller than whatever the light scattering ends at. So that's still way too small. In other words, if it's flat, he's already gone past the knee. So that the knee is where the persistence length is. So means it's right between in the gap. I mean, according to that. Maybe not for the purple one, which I'm not sure which HS. I can't read it the way it's blown up here.
That's just different ratios.
Oh, I see. Yeah. Okay. The plus and minus. I don't know. Anyways, it's good to look at it. You know, I'm not saying that you get the answer, but I thought this was angstrom, and I thought, okay, that matches perfectly. If you do an angstrom, it matches perfectly. But I didn't realize like 1 is too high for angstrom. Yeah. So anyway, it's probably better to have it not agree, because then you see that there's a problem with this paper, you know. it's, I mean, basically every paper, if you look at it long enough, you're gonna start to figure out there's some problem with it, so. I think that's most of it here. There is quite a bit in this, I thought, it's got this diffusion thing, so we'll talk about that later. Like, and we already talked about the time, it goes with square root of time for diffusion, right? Like you have, I mean, the signatures, anytime they're talking about something transport of something, then you're always looking for the distance that you went goes with time to the 1/2, and the prefactor is a diffusion coefficient. We went through that, I think, but so that's Brownian motion. That's Einstein, 1908, whatever. So, and if it's ballistic, you have distance goes with time. That means like protein electrophoresis, which is another one of the papers. You put it into a field, it's got negative charge on it, it flies down the field, it moves that way. Like you measure the motion of a protein molecule. And then he ends up with, I think it's time to the 1/3. This is time to the 1, time to the 1/2 is random. Not random is going more larger, and then he gets smaller. So how do you get smaller than random? Like, can't really do that, So he's got two of these times. You get it from kind of another knee, so you got like it said it's time here. So we'll talk about this measurement. But basically, it's another knee. It looks like it's actually an exponential t over tau for these things, for this correlation function. So we'll talk about what that is later. But basically, he gets this tau thing, and he finds out it goes that the diffusion happens with the square root or with 1/3 for 2 parts. So the 1/3 part doesn't make any sense. So it's just asking, like, how could you get 1/3 out of this thing? The answer might be the same thing, like the experiment's messed up. Or he gives literature. He doesn't explain it, but then he says, like, people have seen it in the literature.
They don't explain it that much either.
In the other paper?
Yeah.
All right. Yeah, because it can't be
They like,
explained.
I mean, a couple of them sort of touch on it, but
Yeah.
they sort of just say,
Yeah.
"What do we see?"
So the main thing of this is, like, when you see something that goes 1/2, you should be happy. Like, it's time to break out the champagne because you figured something out. It's diffusion. And that's the way the world should be. And maybe sometimes you can get this directional motion, but you can't get that thing. So if you see that, then it's time to, like, go back and figure out that there's an experiment messed up. Anyway, so yeah, that's that quiz, I think. So hopefully that'll help. Basically, it's just to get you to look at the paper, like, see where you can go with it. Any other things on it, or I don't know if maybe you haven't even looked at it yet, but is that okay? Or all right. So anyway, we're here. So there's like 2 other size scales to look at in here. Not this. So it's basically the chain alone in solution or in a melt is going to have, like, the Kuhn length, the persistence length. It's going to have some actual step size, and it's got a chemical bond length too, right? But basically, these are the real numbers that would matter. Like you would say, if you can break, like, this translational entropy of the molecule, and there's conformational entropy, it's wiggling around. So basically, if you get down to the Kuhn length, it's not wiggling anymore. So there's no entropy to that, right? So the entropy of the chain comes at sizes larger than that, and how it wiggles, how the rest of the chain can move around, right? So basically, this defines the thermodynamics of the chain. Like if you say rubber elasticity, then you said here. So for rubber elasticity, we said we had, like, the energy is 3/2 times r squared over nl squared. This is the average r squared. And then you say that the force is dr, so you end up with the spring constant times r. The spring constant is 3, there's a kt there too, 3 kt over the average r squared. Right, that's kind of like the modulus. So that's where you get this this is like the molecular weight between entanglements for the plateau. Like when we did log of G versus log of frequency, and G prime goes up to a plateau. So you have like the G double prime reaches a peak kind of. So that plateau is that modulus. It's inverse to the molecular weight in proportion to K2. Right? The same goes for if you take a piece of rubber and you pull it, the bigger the molecular weight between cross links, so that'll be MC, the softer the rubber. Right? So the lower the molecular weight between cross links, the harder the rubber, and the higher the temperature, the harder the rubber. Right? So the modulus goes with temperature because the chain's like a jump rope, and temperature is like swinging the jump rope, and the modulus is like the force that pulls in on the ends of the jump rope as you swing it. If you swing it harder, it pulls in more. Right? So the whole rubber is like a bunch of jump ropes that are pulling in, so you get a higher modulus at higher temperature. It's an entropically driven. It's the same source as you get for pressure for an ideal gas. Pressure increases with temperature. Pressure is proportional to temperature. So anyway, so this is the ideal gas law, and this thing is kind of like this business of this Gaussian chain business. So one of the molecular weight. So anyway, I mentioned that because this packing length uses that thing. So the tube diameter is kind of like an experimental observation. So if you think of, let's see, so the reason to mention these now is because they're size scales that are the same size almost as, they're almost the same number as this tube length. So they're going to be like 10 angstrom. 10 to 50 angstrom, and one of them is like the rigidity of the chain. The other one's going to have to do with, the other two have to do with the melt, right, or high concentration solutions. You have some kind of entanglements. They're going to make a network, and then say you have another chain. I brought a red pen, so not that one. So you have another chain that's the same chain, so it's also entangled, right? It also has like entanglements. So it's the same stuff, but these entanglements of the other chain, you can think of making a tube that it can kind of move in. So it can't move that way, it can only move that way. And it moves that way as if it was a normal chain. So it moves that way by Rouse motion, which you can think of as like a train. Right? So the higher the molecular weight is proportional to the viscosity of it. So once you get to the size scale below this tube diameter, it acts like a train and it just moves through the tunnel. It's a tunnel and it's a train. Right? So that's Rouse motion. Above that size scale, so if the size is bigger than this tube diameter, it's not going to move at all much, right? It's stuck in this tube. So that's where you get this thing about the molecular weight is going to go with the viscosity of the 3/4 power. But viscosity goes with the molecular weight to the 3.4 power, like some huge power. In other words, log of viscosity versus log of molecular weight goes up through the roof, and then it's going pretty easy here. That's the entanglement. So all of a sudden you get a huge impact of it. And this tube diameter governs it. The size scale is about 10 to 50 angstrom. It's the same size. And so there's two sizes. Then the third, all right, so how they found that is kind of complicated. You can do neutron scattering as a function of time. And this is in nanoseconds. So you take the red chain is actually deuterated, and the other chains are hydrogenous. They have the same chemistry, but the side groups weigh twice as much. But the neutron contrast is huge between them. It's like basically red and blue or whatever that was. So basically you can see it, and you can take the measurements on a nanosecond time scale, and you can say, if I take the measurement at time 0 and I take the measurement at time t, at some Q value, so 1 over size, then I see it decays because the correlation between the measurement at time t and at 0 drops. So it's perfectly correlated. So that's 1 at 0 time. Then as time goes on, it becomes less correlated. It becomes random. It could go to 0 if it was total Rouse dynamics. It would go to 0. Right. So anyway, so it goes down. You can see there's a transition between, like, it's kind of shifting, and then all of a sudden, boom, it goes to like this stuff, and that's at low Q. That means it's not moving. Like, it's still stuck at 1. So it's not moving there, and then at these other Q values, it's moving. Right. So between 0.078 and 0.097, which 2 pi over that will give you something like 10 to 50 angstrom, then that's where the tube diameter is. So you can measure it. And then from measuring it, you can plot it as a function of temperature. You find out it's like linear in temperature. You can find out some other features of it. So from that behavior, you can predict. So we'll talk about it later in detail, but just saying there's another size that's almost the same size. It's like 40 angstrom. So it's the same size and it only happens when you have entanglements. Right, this tube thing. So the other thing about it is this tube dilation idea, because the thing's made of itself, so it's the tube that it's in is itself, right? And you're looking at the relaxation of the thing. So it means the tube is also relaxing while the thing is moving through it. So that's a complication that wasn't originally considered. So that's called tube renewal. So if you consider that also, you can get all the answers, like you can predict all the behavior, right? So for the most part. So this tube, this is kind of what DeGennes won the Nobel Prize for. The problem, the only twist to it is DeGennes didn't invent reptation. The guy, Sam Edwards in England, invented it, and he wrote a book on it. DeGennes could talk about it in flowery language. So, and the French needed a Nobel Prize, so they kind of gave a Nobel Prize to him. Edwards became a knight. So that was like his thing. And I guess he kind of got rich or something. I don't know. Can't really feel too bad for him. And he got to complain about it. But, you can take pictures of DNA, you can see it moves through a tube. That's like, the idea is up at so you put it, this is electrophoresis in a gel, it's DNA. And basically this shape up here remains the same, and the thing just weasels through that little hook. That's the idea. The bottom part you're not supposed to look at. It's just this top thing, and it follows the same path. And it's in a mesh of other DNA. So, and then people can simulate it. So you can simulate the tube and do all kinds of calculations about it. So that's one of the two. The other one is a thing called the packing length. So it became popular. It's also like 10 to 50 angstrom. It also occurs only in the melt or in concentrated solution. But it's a number you can use to predict the plateau modulus. So I said like G prime goes up, and then so this is the flow region, and then it reaches this rubber elasticity where the entanglements are governing it. You get a number for this G naught. It's inverse to the molecular weight. Turns out there's a size scale, this packing number that decides that. Okay, and you can map out every polymer in the world. This is just a few, but they've done it. This guy Loshi, who was at Exxon, he's retired now, and a guy named Fetters, who's at Cornell now, who also I think was at Exxon for a while. Those two kind of invented this packing length thing, and it's really useful for polyolefins. But because Exxon makes polyolefins, so this packing length became like universal number. You can predict this plateau modulus if you know like what goes into the packing length, which is basically just the chain density and this R squared and L. So you need to know Kuhn length, you need to know the density of the chain, and you get this packing length, and then from that you can predict the dynamic behavior, from one number. So they thought it was a coup to do that. It's used in the polyolefins. Do you guys use packing length ever? They never use it, so only Exxon uses it maybe. I think Dow uses it, the big boys. So anyway, packing length is a polyolefin number. It came from an odd place though, and it's worth mentioning it. and you can do it in 5 minutes. So it came from this by a guy named Whitten. So Tom Whitten is like the living genius guy. He's really bright. He was at University of Chicago. They wouldn't give him tenure. And then he went to Michigan and they gave him tenure. And then like, he's kind of like has all the ideas, you know. So anyway, he didn't exactly come up with the packing like he did postdoc or something, not postdoc, but visiting scientists at Exxon, gave them the idea, then they took it and then turned it into this other thing, you know. All right, so he was looking at block copolymers. So you have like the A block, the B block. Depending on the length of the A and B, you can get different, you can get spheres of A, you can get spheres of B. If you're equal, you get lamellae, and then you can get rods, and then you can get this double diamond thing in a small region. Gyroid phase, he calls it. So it's a bicontinuous phase, like a sponge kind of. Anyway, so Whitten came up with a theory about how to predict like what's the size of this domains that this thing forms. And it's pretty simple. So it's just based on when there's a boundary region here. So there's a size of the domains that he wants to get, this DAB. Then there's a region here in the middle where the two A and B mix, right? So you can have the energy of mixing. So you can have the average energy of mixing of A and B. So mixing of A unit monomer with a B monomer. Kind of average energy of that. And then you have, you can normalize that by KT. And you can say per monomer. You can define this chi parameters like the average energy per monomer per KT. Right. So that's just like the average, how they would interact. And they're going to interact in a region that's going to be like the area, the cross-sectional area of the chain, then over this little gap region, the thickness of the interface between the two, between the A domain and the B domain. So that's the energetics of, so that kind of opposes mixing. And then that favors mixing. And the other thing is going to oppose mixing is that the chains have to stretch in order to fit into these domains. So there has to be some kind of elastic stretching, which is going to be our business of the molecular weight and then KT, the modulus of that. Or if you, anyway, so you can get those two energies to oppose each other and then write a summation for the energy of this chain and that gap. In terms of this stretching length of the things, you have chi per this is per monomer per KT. This is per KT here, so you just put chi for the enthalpy. Then you have the volume of the chain. So the chain has a cross-sectional area, and then it's got this kind of length DAB. And then you have the other term is the stretching term, which is just KT over R squared. And then the actual length is this DAB, the stretch length squared. So that's R squared, and this is NL squared. And then you substitute in that because the occupied volume is the number of units times the volume of a unit. Occupied volume is also this DAB times that area. You could equate those two and you say DAB is this function. They can plug that in here for you plug that in at the end down here. Here you just take this G and you say, I'm going to minimize it with respect to the area. So area and this length are the same thing. There's just one number because the molecular weight and the volume per unit are constant. So these things are the same thing. The length and that cross-sectional area are related to each other. All right, so you take the derivative, set it to 0, find the minima. You can solve for the area. Then you can plug that area into this equation, get what that thickness is. Then that solution like is verified by experiment. So it's just like a simple balance between the energy at the interface and the stretching energy. So you can see that rubber elasticity thing comes up everywhere. Like every time anyone does anything, it's that same equation. Anyway, so Witten figured out from that, Witten did this, and then he figured out there was a number, this packing length number, which he called the intrinsic elasticity. Later by Loesch was called the packing length. And it has to do with kind of the lateral size almost of the chain. He got interested in this thing, like that this number meant something. So it ends up that it's just like the ratio of the monomer volume to the Kuhn length squared. So that ends up having a unit of length. It doesn't really mean much, but it ends up being an interesting parameter that has units of length. It's from 10 to 50 angstrom. Then in the end, that number can be calculated for anything pretty easily. If you know the Kuhn length, the density, the mass of a monomer, the length of a bond, chemical bond, and then you can plot out like that business for it. This packing length becomes like the governing number for everything. So I'm just mentioning that here because it's the same length. You have like the Kuhn length, the packing length, the tube diameter. They're all the same length, like the same size scale. You can measure the tube diameter, you can measure the Kuhn length. The packing length is a little weirder. But rheologists like the packing length. That's the one they want. And the other theoreticians like the tube diameter. And some simulation people are simulating rheology, and other people like the Kuhn length, I guess, biologists, whatever. So they're different things, but they're all the same size scale. All right, so next time, like we'll start on long range interaction stuff. Kind of what happens when the chains interact. So, all right. So,